Hello everyone, and welcome to the first morning session in this room for the day. Next up, we've got a long technical deep dive, so if you're not prepared for 70 minutes?
70 minutes.
70 minutes of really interesting topic, then get ready. So we've got Mark Smith presenting It's Pythons All the Way Down, Python Types and Metaclasses Made Simple.
Hello everybody. Thank you for coming to the talk, and congratulations on dedicating yourself to fully understanding Python's kind of deeper magic. This is maybe the start of a wonderful journey for you into building things that work in ways that people don't expect. Maybe I can help with that. So in a moment, I'm going to talk about Python types, descriptors, metaclasses. I am going to hopefully make them simpler. Simple is a very bad word to put in a talk, especially about a relatively arcane topic, because it essentially means that people coming from different backgrounds, some people will find it simple, some people will find it immensely complex, and both of those points of view are valid. So I'm kind of wishing I hadn't put that in there. It's in there. Maybe simpler is a better word. But before I start talking about descriptors, metaclasses, and deeper Python magic, first I'm going to talk about something more important, which is me. My name is, I'm known as GD2K, more or less everywhere online, GitHub, Twitter, etc. But my real name is Mark Smith. I'm a developer advocate for Nexmo. We are a sponsor of the conference. I live in Edinburgh. I run the local Python user group. I'm also an organizer of EuroPython and PyCon UK, and do a bunch of other stuff. Okay. So you may not have heard of Nexmo. Could I just have a quick show of hands who has heard of Nexmo? Awesome. That's why we're here. We are I won't talk, this is a commercial break, I won't talk about this for too long. We are we provide a set of web-based APIs that allow developers to write code that sends and receives SMS messages, makes voice calls, does video streaming, sends messages via WhatsApp, Viber, Facebook Messenger, basically any type of medium between any type of platform. That's the idea. If that sounds interesting, please do come and talk to me afterwards. I have voucher codes that will get you set up and running with some credit. But that's enough about me and Nexmo, almost. So this talk has a bit of a history. Goes back 8 years. So 8 years ago, when I had only been a professional Python developer for a very short time, for some reason I decided to give a talk at EuroPython called A Deep Dive into Python Classes. But as part of the abstract, I specifically said I won't be talking about metaclasses, because I didn't want people to be disappointed. The main reason I didn't want to talk about metaclasses was because although I had written a couple, I didn't really know how they worked, and I certainly wasn't confident talking to other people about them. So it's now 8 years later. I've written a couple more. I understand a little bit more about them, but I wanted to know the nitty-gritty, and the best way to know the nitty-gritty about something is to give a talk on it, to actually do that research. So this talk is basically the result of all that research. So here we go. The basic talk is divided into 3 sections. First, I'm going to talk about Python types, which is a conceptual idea more than anything else. I'm going to talk about Python classes, which is Python's implementation of types. And then I'm going to talk about Python metaclasses, which are kind of an underlying layer beneath classes and how they work. I will stop specifically for questions at the end of each one of those sections. So if you have a sort of something that you haven't quite understood in that section, like please, you'll get a chance to ask a question. It will also break up the talk a bit. It's a very long session. But if you have a question, just while I'm in the middle of speaking, if I'm not explaining something very clearly, or you're just not quite managing to keep up with some of the concepts, feel free to stick up your hand and ask me a question. Don't wait for a microphone. I will repeat the question. And then hopefully we can keep everybody kind of moving along for the whole session. If you don't understand anything that I'm explaining fully, you will not be the only person in the room who doesn't understand it. So really build up that confidence to ask the question. Other people will appreciate it. So starting with the first of 3, Python types. I am not a computer scientist. I dropped out of my computer science degree. And so the first thing I did when I wanted to talk about Python types was to Google typing in. And I came up with this definition on Wikipedia, which kind of matches my own understanding. In computer science and computer programming, a data type, or simply type, is an attribute of data which tells the compiler or interpreter how the programmer intends to use the data. A data type constrains the values that an expression, such as a variable or function, might take. The data type defines the operations that can be done on the data, the meaning of the data, and the way values of that type can be stored. I can summarize that essentially as a type in Python defines the capabilities of a piece of data or a group of related pieces of data. It constrains what can be done with that data, so it tells you things that can't be done with that data, and it ascribes a semantic meaning to that data. So this is more a conceptual idea. It's something that's useful for the developer more than maybe the interpreter. And I'll touch on that in a moment. So just to go into those in a little bit more detail, a capability is something you can do with some data. And here are two ints, and I'm sure everybody in this room knows that you can add two ints together and it returns you a new int. This is a capability of the int type that you can use the addition operator with them. And if we look inside int, we can see how that capability is defined. So we use the dir function on the int class, and it gives us a bunch of stuff, which would just fill up the screen. But the main thing that's important is that there's an attribute on the int class called dunder_add. And Python uses this behind the scenes. Every time you call add, it is calling the dunder_add method on the left-hand side. There's some exceptions here as well, but this is the simplified view. So this is how the capability of adding numbers together is defined in Python. This is what Python's doing behind the scenes. So, constraints. One of the constraints in Python 3 is that you cannot add an integer and a string together. You get a type error. It has tried to add these together, and essentially that method has raised this error for us. So this is something you can't do with the data because either the method isn't defined or the method has explicitly thrown an exception to say you can't do it. And then the third part, meaning. As I say, this is a more conceptual idea. Let's say we have a variable called d, and we don't know what it represents. But if we call type on it, the type function will return us the class that is sitting behind d, essentially the set of meaning behind this variable. And we see that it's a datetime, which means that we know, by reading the documentation about the datetime class, that d is a representation of a point in time. And so we can do operations like move it forwards in time, backwards in time, and we can express it in different string forms, things like that. So this is meaning for the developer. It's useful for debugging and just kind of tracking the way data is moving through your program and what that data means. Alternatively, we might have a variable p. We don't know what that is, so if we call type on it, we can see that it's a functional method, and so we know this encapsulates some executable code, a set of operations that we can pass some data to. It will conduct some operations on that, and potentially some of the global state as well, and maybe return us a new value. So this is, again, even this has meaning, like a really low-level data type, like a function, has meaning to us. We are meant to execute this. Constraints and meaning go hand in hand. Newer programmers are sometimes upset that they can't, for example, just concatenate a string and an int. Other languages do allow this. But you end up with this, again, with meaning. Like, what does this mean? Are we trying to convert both of these to numbers and end up with 24, as we did before? Or should we convert them both to strings and end up with the string 1212, which I have in here somewhere? So with the literals at the top of this, the first expression here, it's really obvious, maybe, what we probably want from this. But when you have two items that you've, say, read from a database and you don't necessarily know what types they are, you probably don't want one of them to be coerced into another type and then the operation conducted because you don't know what the end result is going to be. You don't know whether you're going to end up with a sensible expression or whether you've just got the wrong bit of data back and you've now like munched them together in some way that doesn't make sense. So it's good that Python is strict about this, in these cases at least, because it doesn't know what decision to make. It doesn't know what decision you wanted to make with these random bits of data that are flowing through your program. So it plays it safe and tells you you did something that doesn't make sense. So it's up to you to explicitly turn the string into an int by passing it, or to turn the int into a string by essentially passing it through the string function. So Python has quite a few core types. They're described in a document called the data model. These are the ones that people tend to interact with day to day. There's 8 of them. A Boolean expresses true or false values. We've got integers, which are numbers without a fractional part. We've got floating point numbers, which are numbers with a fractional part. Complex numbers, which are just like some sort of weird idiosyncrasy about Python, that it has a core type that represents complex numbers. We've got byte strings, which are an array of bytes. We've got string, which is an array of Unicode code points. We have functions, which, as I said before, encapsulate executable code. And we've got class, which is actually like a bigger topic, which we'll be covering later. Class is essentially Python's expression of custom types. They're your way of creating new types in Python. And we'll cover some of the details of that in a bit. If you call the type function on values, like instances of each of these types, it will hand you back the type, essentially the class of that piece of data. So you can see if we call it on true, we get back a class. Although this is being expressed with like a less than and greater than either side of a string, but that's actually a class value there. So you can introspect it as a class. So we've got the bool class, float class, complex, etc. We don't really have expressions for functions, so I've had to define that as a statement. So I've defined a function called fun. If we pass that to type, again, we get a class function. So even executable code has a class behind it. So this is a fundamental building block of Python. And then I apologize for this. I thought this was funny when I wrote it, the class war. So I'm going to be using the word war a lot in the next couple of slides. So if we call type on our war class, the type of a type is type. This is part of Python's slightly nasty way of dealing with metaclasses. This is also our first glimpse of metaclasses. Everybody say, ooh. For the benefit of people watching the video, they all said, ooh. So we've got the type of a type is, a type of a class is type. Type itself is, in fact, a class. So I've been calling it a function, but it's not a function. It's a class. And the type of type is itself type. This is how mind-bending metaclasses get quite quickly, which is why I've broken this talk down into a 70-minute talk on various different aspects that lead up to how metaclasses work. But this is definitely like probably the single most mind-bending part of how type works in Python. So, yes, I'm just going to show you another idiosyncratic thing about Python, which I think expresses something that's useful to know up front. So the type of our class, war, is type. And if we call it, the type of type is type, as I just mentioned on the previous slide. So those have the same capabilities and constraints, because those are expressed in types in Python. So we should be able to do the same thing with them. And classes are mutable, which is kind of a fundamental thing about them that maybe we probably shouldn't be taking too much advantage of, but I'm going to show you some ways to do that during this talk anyway. So here I've just added an attribute to our class, war, with a nonsense value. And now if we look inside using the dir function, we can see that our useful value has been added to our class. So we can, because it's got the same class as, because it's got the same underlying type as type, we can do the same thing with type, except that we can't, because type is not mutable. Type is implemented in C. It is a built-in or extension type. So although it looks like the same type, it behaves in many ways the same, it is not quite the same. And this is really another aspect of Python. When you write a Python program, every expression in Python is being executed by the Python interpreter, which sounds really obvious, but my point, and you'll see various examples of this during the talk, is that Python does things for you that you don't always know about if you don't know exactly how Python executes code. Python is always trying to help you out. It is much more powerful under the hood than you may first expect when you're learning how to write basic Python programs. So that is the end of the types section, which is the shortest section of the talk. Does anybody have any questions at this point? Okay. So there are more things we could cover about types. As I mentioned during this section, classes are Python's expression of types within the language. And so we will definitely be covering some more of these concepts during this section. So a useful question to ask ourselves when talking about classes is, what is a class? I found classes, I learnt Java back in the 90s, and it took me weeks and weeks of writing programs with classes in, because you can't write Java code without classes, again and again and again, just using them until one day they clicked, and it was like, oh, I get what classes are for, I get what instances are, I get how they relate to each other and how I might use them to build programs. I'm not sure, when you come to Python, I think you see boilerplate code a lot, and you don't have to work with classes immediately, and I'm not sure everybody asks themselves this question up front, so I'm asking it now. So a class and types themselves are different in dynamically typed languages and statically typed languages. A dynamically typed language like Python tends to encapsulate a bunch of behaviors, as I said earlier, in a class, or a set of classes that relate to each other. In statically typed languages, they also tend to be a restriction. You can also get this with type hints in Python, where you have a function that will only accept a certain type, or a type that implements a certain interface, that kind of behavior. So it becomes a much more important thing how you structure your classes, because if you want to call a certain function, you will need an instance of a specific class, so you may need to inherit from it, etc. Python is much more flexible. With duck typing, as long as a type looks a bit like the thing that is expected, then that function should operate on that data as expected. So in Python, a class is just a structure used to define new types. It's less of a kind of integral thing in the language. It's really a set of instructions for creating an instance. Right? So you will have a one-to-many relationship, you'll have a class, and then you'll have many instances of that class. A class is a callable, much like a function, and it returns an instance. So I don't know that everybody always thinks about that, is that a class looks like a function. That's kind of important. And on top of this, as well as just being a function that returns an instance, it also provides behavior. The class hangs around. So an instance maintains a reference to the class that created it. It's used for looking up methods which provide behavior, but they belong to the class and not the instance. And this is because Python is secretly a prototypical language and not a classical object-oriented language. So yeah, there's some conceptual stuff there that I'm not going to go into, because we only have 70 minutes. So, to my mind, a class is a thing for constructing instances. I don't really like the word object, because both classes and instances are objects in Python, as I just mentioned. In fact, when we get to metaclasses, you'll see that the distinction between classes and instances is largely arbitrary. And so the word object just means anything. I will be using it from time to time, but it is literally like the broadest, vaguest term for a thing. I use the word thing interchangeably with object as well. So a class is a thing for constructing instances. So here's a simple example. I defined a class called car. It has an initializer function, which just takes a value and sets it on the instance, which is self. And then I've got a drive function, which just simply prints out a message when you call it. And then the last line instantiates it. So it creates an instance of car, and passes it the value red, which will be stored away on that instance. So then when we look at the instance, if we just print it out, we can see that, hey, we've got, it says object, just imagine that says instance there. And we can look inside the instance, and we can see a whole load of stuff there that we haven't defined that we've got for free. But the important thing is at the end, we've got color and drive, the two things that we defined. One, the color is on the instance, and drive is on the class. So if we look inside the instance dictionary. So unless you've implemented slots, instances store all their attributes in a dictionary called dunderdict. So in this case, we've got this dictionary. It contains the one item that we set on the instance, which is color. But where is our drive function? Well, if we can look up the class. As I said, instances maintain a reference to their class in the dunder class attribute. So this is now a class, car. If we look inside there, that also stores its attributes inside a dictionary called dunderdict. And if we look at that, first, there's two things to note. First is that it returns a mapping proxy, not a dictionary. So it's a read-only dict. I don't know why they did that, guessing it's an optimization. If you want to add stuff to a class, you totally can by just using a full stop or a period to assign an attribute to that class. And the second thing to note is that we have our drive function in there. And I do want to highlight, I'm using the word function very specifically here, and I will come back to that later. Drive is a function called car.drive, not a method. the class also stores the base classes that it inherits from. I didn't specify any classes to inherit from, so by default it just inherits directly from object. So you can see if I refer to the dunder bases attribute, this is a tuple and it just contains one item, which is our object class. So this is our inheritance hierarchy, or helps define our inheritance hierarchy for looking for things that are defined on instances. And I'm going to get to that in a minute. Oh yes, and here if we look in object, because object is the thing we're inheriting from, if we look inside that dict, then we can see all the other stuff that was on our instance. You remember when we did dir on instance, it flattens everything that's in the instance and the entire class hierarchy into one dictionary. So just for ease of access, really. And the other thing to note, as I said, is that usually classes are singletons. So we've got object at the top, there's one class called object, there's one class called car, and then we could instantiate that multiple times. But they all refer to the same car. So when you call drive, there's only one drive function, and it's defined on one instance of car. So we haven't got, if you define a class with lots of behavior, that's not duplicated if you create 1,000 different instances of that class. So looking briefly at how we define classes, I suspect most of the people in the room really know this stuff, so I'm not going to cover this in huge amounts of detail. This is what a class definition looks like. You give it a name and an optional list of parent classes, direct parents. You can define a dunder new function inside that class. This is a class method. It's a special case class method, so you don't need to declare it as a class method. So it takes the class as a first parameter. The class has not been instantiated at this point. It is the job of dunder new to instantiate the class, to create an instance, do whatever it wants to with it, and then return it. By default, you are calling objects dunder new function, and it will return you a new instance of the class you provided it, which is your class. And it won't be initialized at this point. So if new returns an instance of the current class or a subclass of it, it will then be called, init will then be called. So init is the next function I'm going to cover. If you can return anything you want from here. If I'm defining a class, I could return a string if I wanted to. But if I return a string, it's my job to initialize it. It will not be initialized by calling the dunder init function. Dunder init, as I said, the initializer function. So the instance has already been created. It has nothing set on self. This is where you would set all the instance attributes, that kind of thing. So let's talk about inheritance. This is going to take a while. You may not expect it to take a while, but I think it's justified. So what happens when you get an attribute? Certainly the diagram I have in my head looks something like this. So we look on the instance. If it's not on the instance, we look on the class that was used to create the instance. And if it's not on there, we go up the hierarchy of superclasses. And if it's not found on any of those, then it raises an attribute error. This is overly simplified. So let's make it more complex. So first, there's dunder get attr. So if you define this, this acts as a fallback attribute accessor. It's past the instance and the name of the thing that you're asking for. And you can do whatever you like in there. So basically what happens is, if it looks on the instance and doesn't find it, and it then looks up the class hierarchy and doesn't find it, just before it throws the attribute error, it then calls dunder get attr, which can do anything. It can go to the network, it can load files, it can do whatever you want, and if it can generate a value that makes sense to the user, it can return that, or it can raise the attribute error. Then there's get attribute, which looks very similar, but is really quite different. You don't want to mix these up. So this is called before anything is looked up on the instance. It's defined on the class. It goes here at the top. So before it even looks in self to find something, the first thing it will do is call dunder get attribute. And dunder get attribute can return whatever it wants to. So this overrides essentially all the behavior of looking on the instance, going up the superclass, things like this. You're actually calling this anyway because this is defined on object. So this is your way to completely magically change the way attributes are kind of defined, the way they're looked up on an object. It's unusual to use it. It's also really easy to write a recursive version of this function that just calls itself until the interpreter crashes. If you raise an attribute error, it will jump straight to dunder-get-atcher for your kind of fallback function. So really, it does kind of bypass all the other behavior in this sort of this cascading sequence of operations. So I'm just going to take a brief break from this diagram. It is going to get more complicated. But first, we've been talking about going up the class hierarchy. And I think we all at least vaguely know how classes work in a hierarchy. It gets complicated if you if you're using multiple inheritance to extend from 2 classes and they extend from the shared base and things like that. But there's a well-described algorithm for how we traverse that graph of superclasses. And getMRO will essentially return you a flattened list of, this is the order through the superclasses that I will go to try and find data. Could be useful. It can also be overridden, and I'll show you how to do that in a bit. Super is a function that essentially provides you with an object that you can look up attributes on, and it will look through the hierarchy using the getMRO order to return you value. So essentially, it looks on the instance, and then actually it doesn't look on your current instance or current class. It looks on the superclasses and above. This used to require you to pass the current class and the current instance into it as parameters. If anybody's done any Python 2 recently, will easily remember. It still does. Behind the scenes, what Python does is when it finds a call to super, it rewrites the bytecode to pass in those parameters. There's a special value assigned to functions that allows it to find the class that a function was defined upon. So really, actually, nothing's changed. This is just, they've done some syntactic sugar to sort of change the way that you actually write this, which is great because it was really ugly and complex before. So now let's talk about descriptors. Can I just have a quick show of hands? Who knows how descriptors work? OK, that's good. So you remember what I said earlier about Python doing things for you. Descriptors are kind of the ultimate example of that, in my opinion. So this is where we are so far with understanding how attributes are found on instances. But in the Python data model, there's a description of more rules that need to be assigned to this diagram called the descriptor protocol. So it's essentially a set of rules or a set of behaviors that are encountered. It's kind of how Python works underneath the hood. And I think before I explain how they work, I think it's useful to describe what they're for. And 3 of the things that descriptors are for are to allow these decorators to work. So if you used property, class method, or static method, they change the way that data is accessed on a class or an instance. So property used to decorate a function, and it means that when you then access that attribute, it calls that function behind the scenes and then returns you the result. And this sounds like sort of dark, specific Python magic. It's like maybe you couldn't implement your own property decorator if you wanted to, but you totally can. It's pure Python, and I'm going to kind of show you how that works, or at least the way it works. And then class method and static method, if you think about it, you're defining a method that either takes a class instead of self or doesn't take class or self in its parameter list. But when you call it, you are definitely passing in that self. Even though you don't see it, you're calling it the same way as you call an instance method in many cases. But somehow, when the actual function gets called, that data has been manipulated or removed. So again, it's changing the attribute. It's kind of creating a wrapper around that attribute, the method, that when you call it, does some stuff before actually calling the underlying function. So now I've talked about why we've got descriptors. I'll just talk about how we do it. So a descriptor is an object with binding behavior, one whose attribute access has been overridden. So this is the specific phrase. There's a way to override attribute access. So we've seen a way to do it globally per class using getAtter and getAttribute, but this is specifically per item, so it's per attribute. If the attribute defines dunderGet, dunderSet, or dunderDelete, then it's defined as a descriptor. It is a descriptor, and so Python will do different things when you access this on a class or in an instance. So here I've defined a descriptor. It defines dunderGet, so it is a descriptor according to the previous definition. And now I'm just defining a class, just an ordinary class, and I'm assigning an instance of that descriptor to the getMe attribute. And then here, I'm creating an instance of the class, and then I just access getMe. And what you'll see is that that string that's returned was generated by the dunderGet method. So we haven't just accessed something on the dict. What we've done is we've called a method behind the scenes. And this is how the rule works. So basically, it's what you'd kind of expect in the hierarchy, so where we're traversing for data. So basically, if we find the attribute in the class definition, or one of the superclasses, if it defines done_get, then Python won't return you that value. It will call done_get and return you what's returned from that. So in many ways, it's like a property. If you think this is actually the underlying mechanism that property uses to define itself. So it wraps a function, calls the function, returns you the data instead. Who knew this already? I've got a few hands. Who knew that there are two different types of descriptors and they behave completely differently? Hand up from the person who's also giving a metaclass talk in the next few months. So what we've just defined was a non-data descriptor. If you define one of the mutation functions, so set or delete, then you have a data descriptor. The terminology is not that important, but the idea is now you have an attribute that you might want to, you're overriding the sort of mutation behavior as well as just the accessing behavior. So let's define a data descriptor. So here we've got another, it's the same, I've added a set method to it. It doesn't go in the same place in this order of operations. It goes just after done_get attribute. So it's just before the instance value. So this is actually accessed before looking up anything up on self. And the question you might be asking yourself is, why is this so complicated? And the answer is relatively straightforward. It's methods. So I've been very specific about the way I've been describing executable attributes defined on a class. I've tried to be very specific anyway. So we've been defining functions on the class. And you'll see from the first line here that if we refer to drive on the class, we get a function. That's what I've been calling it. That's why I've been calling them functions. But if we refer to it through the instance of car, my car, then we get a bound method. And you can see there's actually two bits of data in that string. It says it's car.drive, so that's the function, and it's also bound to the car instance. So what's essentially happened is you've passed it enough data that it's handed you back a wrapper object. So a method is a wrapper object around a function that it doesn't require self. Self was bound to that object just as you accessed it. So if we look back at the original definition of get, here, it takes the instance and the owner, and it's instantiating a method that contains the instance, so that when you then call that, you no longer need to pass in the instance. That's where self comes from when you call a method. If anybody's ever been confused by that, this is where self goes. It gets kind of stored away in the actual method you're returned, so that when you call it, you don't need to pass it in. So, attribute lookup in Python is actually quite complicated. You can see that it switches backwards and forwards between checking in the class hierarchy and checking the instance. It's not a simple matter of looking at the instance and then falling back to this hierarchy of classes. So I don't know about you, but this is what goes on in my head when I think about instances and classes. It's like instances sit below classes somehow, and then you kind of go up. I mean, you could flip it the other way around. It doesn't really matter which direction this goes in, but I always think of it as linear. But this is not an ideal way of thinking about it, especially as we move on to the next section. The way I would like you to start thinking about this is as two dimensions. So we have the classes, which are in a hierarchy. We have instances off to the side. They actually sit slightly apart from the class hierarchy. And this will be more useful as we move on through the next section of the talk. So that's the end of the classes section of the talk. Does anybody have any questions? Okay, I've either lost all of you or I'm keeping you along. Yes? Okay, so actually it's not a type, sorry, I'm probably mixing up the terminology that I'm using. So the first one, that's actually a class. Sorry. Yes, so the question was, before I was talking about functions having a class of function, whereas now I'm talking about the type of a function as being a function. Is that right? I'm getting a very careful nod there. So yeah, no, actually, I'm not calling type on this. So although I'm printing out car.drive, and it's just kind of saying, yeah, this is a function. If I was to call type on car.drive, I would get the class function, if that makes sense. Yep, awesome. So, any more questions? No? Okay. Python metaclasses. So again, I would like to talk about why we define metaclasses before I start talking about them, because again, they're added complexities. Why would you add extra complexity to a language? So it's useful to know why are we adding extra complexity to the language? What does it allow us to do? So there's a handful of things here. There's probably more. But these are things I've seen in the wild in real metaclasses used in real frameworks. So we can register a class on definition. So we've got some sort of central registry of a specific type of class. So the metaclass just kind of means that every time you instantiate one of these classes, it says to some central authority, hey, there's a new instance here you might be interested in. Django uses this for registering models. So then when you can run the Django command to say, like, create me a database, and it will go through each of your model definitions and create a table for that model. So this is useful. We can initialize attributes. So this is a common pattern for metaclasses, where it just loops through all the attributes that have been defined on the class and just tells each attribute what its name is. Because if you think about it, when you're calling the function or the class to define a thing, it doesn't usually know its own name. And it would be duplication if you kind of said ID equals new ID field, and the same ID. It's the ID string. So yeah, you have to do this kind of thing with named tuple, for example. But inside classes, you don't have to, because you can use a metaclass to set this for you. So we can modify a class based on its definition. We can add things. We can remove things. Again, you could go through the attributes and form an extra attribute that just contains a list of special types of attribute inside your class to make it easier to use. You can ensure that a subclass is implemented correctly. So after you've actually instantiated the class, you can just go through it and say, oh yeah, they've defined all the things they needed to. That could be useful too. I haven't seen that used as much as I think it could be. I think it could be really useful. Sometimes it can be tricky to kind of implement a subclass correctly. And I think metaclasses could be a useful way of kind of ensuring that things are being implemented fully. And you can totally mess with the way a class behaves. And I'm going to show you some of that magic too. So before we start talking about how we really define metaclasses, I want to talk about type a bit more, because we talked about the type function, then we talked about the type class, and they're the same thing. And we've seen the first version here already, where we pass type an object, a class or an instance, and it tells us the type of that thing. So if it's a value, then it tells us the class, and if it's a class, then it tells us the type, essentially, the class of the class. But there's a second form, which I've got up on the screen here. The second one is it will create a new type. It is a factory for new classes in Python. So you call it with 3 values. The first one is a string containing the name of the class that you want to create. The second one is a list or tuple of the direct parents of the class. So much as this is basically equivalent to a class declaration, if you think about it. And then the third thing is the class dict, which is a dictionary of the things you want inside the class. So you can add functions, you can add class data, anything you want in there, and it will essentially, this is what class is syntactic sugar for. So to give you an example, this is equivalent to our car class that we had earlier, but using type to do it dynamically. So I've created an init func. I didn't call it dunder init because that would be a bit weird at the top level. In fact, I should start at the bottom, really. So the block at the bottom is creating this car type. It's passed 3 parameters, as I said, name of the class, the direct parent is object. We could pass it an empty tuple because that just gets added in automatically. And I've passed it in a dict with an init function and a drive function. And obviously I haven't defined the init function with the same name, but it doesn't really matter. It's the way it's looked up is on that key, not the value. So this is identical to what we had before. It's a lot uglier. There's a reason for having class syntax in Python, but it is also really powerful, and I have seen it used in the wild. I'll show you an example in a bit. So just imagine we had 3 mix-in classes. They're not related to each other. None of these inherit from each other, but each one provides behavior. So in this case, I've got A defines an A method, B defines a B method, etc. Imagine you needed, for some reason, to create combinations of each of these, every possible combination of 2 of these. So an AB, an AC, a BC. Imagine you had 6 of them or 12 of them, and you need to create all those classes. That would be horrendous code. You would almost certainly, if you really had to do it, I mean, first you would say, why am I doing this thing? So then you would probably write yourself some Python code to generate Python code, and then you would paste that into your project. It'd be horrendous. But Python is a dynamic language, so we can do this dynamically. And so we can do it in 3 lines of code. After we've defined those classes, you then use iter-tools to go through all the pairs, the combination pairs of those classes. We can create a name dynamically out of those class names, and then we can assign it to the global dictionary, so the current module's dictionary. And this is all a bit deep magic, but hey, you came to a class on metaclasses, so what did you expect? So that means that then there's a class called AB suddenly in my namespace, and I can look at the bases, and I can see it inherits from A and B. I can instantiate it and create a variable of that type. I can call A on it, and it does what I expect. I can call B on it, and it does what I expect. And I can call C on it, which will fail because it doesn't inherit from C, and so it doesn't have a C method. And this is actually crazy powerful. I can see some really interesting use cases, like vaguely out there, for sort of creating matrices of classes because inheritance is kind of limited in some ways. In its kind of pure form, how you define it, whereas being able to create a set of classes out of a matrix could be really interesting. So back to what is a metaclass. Now we've talked about why metaclasses a little bit. It's a callable that returns a class, and it literally is. So a metaclass doesn't have to be a class. Yay for consistency. It can be a function. So here I've got, as I said, stupid metaclass. It's in the name. And this just defers to the type function and returns the result. But I can use this in the class definition. I can say, this is my metaclass. Here's a function. And that will get called to instantiate the resulting class. The only problem is that when this is now no longer the class of a class. So stupid metaclass, really that last line there should say class, stupid metaclass, because that was what I defined in my class definition. But because actually type was used to create this class, I've got the wrong metaclass there. So I've used it to create a class instance. I could have done some weird stuff in that function. It could be useful. But fundamentally, it's not related anymore. Like it's a fire and forget way of creating a class. So people say this jokingly, like a metaclass is the class of a class. Simple. We all understand metaclasses now. But it is genuinely useful. We've been talking a lot about inheritance and how classes relate to instances. And if we go one level beyond and think of our class as being an instance of a metaclass and just kind of blur our eyes a little bit, it's the same pattern. If we understand how instances relate to classes, we can also understand how metaclasses relate to classes. And I'll get into some more detail on that in a moment. But this is a really, again, it's a stupid example, but this is a sort of base implementation of a metaclass. So we have a class that extends type, because type is analogous to object. So object is to classes as type is to metaclasses. And then we can use our new meta class in our class definition, and then we can actually instantiate that class. And unfortunately, I've really messed up the slide, because in the previous slide, I told you what the type of my class was, and I told you it was wrong. But in this slide, if we did type on my class, what we would get back is my meta. So they're actually related. So as I said, it's a class of a class. So if we were to look at my class dunder class, it would specifically point to my meta. I'll show you a diagram that I think illustrates it in a moment. But before we get to that, I will talk in slightly more detail about how we define a metaclass. So much like defining classes, we use a class definition, because it is just the class of a class, but we inherit from type, as I said before. Now, there's this slight complexity in the way that metaclasses are initialized. They are not quite as simple to define as classes. So there's a 3-step process. So before new is called, so there's still new and init, and I'll go into those in a minute, but before those are called, have dunder prepare is called on our metaclass. if we've provided it. And the only job that this has is to return a dictionary that will then be used to contain everything in the metaclass. Sorry, to contain everything in the class. This is our factory for creating classes, remember. The reason for this is simply so you can pass back a special implementation of dict. So if you wanted, if for example, the order that your attributes were defined was important, you could pass back a dict that, as well as storing away the things that are added to it, also recorded the order that they were added. Then that would then, it allows for more expressiveness in what your metaclass can do when creating the class ultimately. Normally you will ignore this unless, as I said, you care about the order that things are defined on your class. Then we have new. So new is analogous to new on a normal class, but it takes more parameters. So this is similar to what we just saw when we called type. We've got name, basis, and class dict, and obviously it's passed an instance of this meta class as well. And then we can pass in optional keyword arguments as well. I will get into where they come from in a moment. So again, the job of this is to create the class. So usually this will call super new, which is equivalent to calling type, essentially. But it might do some stuff to the class dict beforehand, because the class dict gets passed in. So you might then filter out things you don't want in your class, or you might add things in that you want in your class. Essentially, it's manipulating the input data to the class. Or when the class is returned, you can then manipulate it in similar ways. So that's what init is for. Init is for post-processing of your class. If you don't really care how it's created, but you want to remove a couple of things, this is where you would do it. Keyword arguments are interesting, and I think they're underused when people do write metaclasses. So metaclasses normally don't take any parameters, and they just do the same thing to any class that they're asked to create. But in theory, we can pass parameters through. So I'm going to start at the bottom here. You can see I've set the meta class, and then I've set this magic private keyword argument. And private is not special. I could call that foo if I wanted to. And all that happens is then that is passed through to new and init when the class is constructed. And it's up to the meta class to decide what to do with that input data. It's just like a parameter to a function, right? So it means we can have a meta class. In this case, maybe the meta class strips out all the dunder attributes before creating the class. If you pass private equals true, or maybe it doesn't. If you don't pass private equals true, no, you have many options here. This is just another powerful feature of metaclasses. So I'm going to update the diagram that we were looking at before, not the big complex one, but the one where I was talking about how instances and classes relate to each other. So here we have our classes. And I've purposely colored these blue so they look a bit like blueprints. So the classes are blueprints. People think about classes that way. But it gets more complex when you start thinking about metaclasses. Maybe a metaclass is just a pen and paper or something like that, some sort of pre-blueprint. I'm not really sure. But here we can see how type relates to object and car. Now, this is in the case where I haven't defined a custom metaclass for car. So they are both instances of type. Type is the class of object and the class of car. And then car is then the class of my car. If we define a custom metaclass for car, then it starts to look like this. And you can see why we need this extra dimension, right? We've got two different class hierarchies here. We've got the class hierarchy, and then we've got the metaclass hierarchy with type at the top. So now let's talk about class attribute lookup, because we were talking about instance attribute lookup before, and I just want to go back to the big complex diagram, but talk about how it works when you look up things directly on a class rather than going through an instance. So this is basically the same diagram as before, except everywhere it had class before, it now says metaclass, and everywhere it said instance, it now says class. So we're just coming into that diagram at a different point, right? We're just coming in one level to the left. And it works more or less the same with one caveat. So descriptors still work on the class. So when you access a descriptor on a class, it still calls dunder get, for example, but it passes in none as the instance. So in this case, whereas we never call descriptors on an instance, they do get called on a class when you're doing class access for a descriptor. It's just one extra step. It's basically the only place where it's not consistent between like moving from looking things up on an instance and classes and looking things up on a class and metaclasses. But it's really important to note here that we are looking stuff up on the metaclasses. If you look, metaclasses are part of the inheritance chain. So if you define a method, or sorry, a function on a metaclass, then you can end up calling that. If you can access it via the class. So it looks at the class, which is our instance, and it also looks at the metaclass, which is our class. So it goes back to our definition of metaclasses are the class of a class. It's a horrible description, but it is helpful. I've been using metaclasses for nearly a decade, and I only realized that this year, that I can actually call stuff on the metaclass like, through the class, almost by accident. So yeah, you're actually affecting class behavior, like just how, what you can do with a class by defining things on a metaclass. So if any of you are like me and slightly evil, what you're thinking to yourself is, well, when does this diagram stop? It's like if instances have classes and classes have classes, what do metaclasses have? Do we have metaclasses? And the answer is yes, kind of. So we have the type of a class is type, the type of type is type, and the type of type is also type. So that last diagram we were looking at actually looks like this. I apologize that there's some overlaps there. So you'll see type is an instance of itself, and car meta is both inherits from type and is also an instance of type, which I know this really doesn't help with the idea that I was supposed to be making this simple. You can mostly forget this, but it's also worth noting that you can kind of override some of these relationships if you want to. If you want to change the way that car meta is created, you can create a meta class for it. I believe it will work. I haven't tried it. There's only so much my mind will take. But fortunately, because of this weird magical relationship that type has to itself, this diagram doesn't naturally go off to the left as far as you want. There's not a sort of meta type or anything like that, because they've decided to kind of encapsulate it in this one type. But it doesn't help with the confusion. Like when you start talking about things being instances of themselves and inheriting from themselves and things like that, it's a bit of a mess. It also doesn't help that type has two completely different behaviors, right? I meant to talk about this earlier. It's like it really shouldn't have two completely different behaviors. I personally think that was a design mistake when they implemented new style classes in Python 2. But I haven't had any discussions with anybody involved in those decisions, so it's entirely possible and probable that I'm wrong. So let's go back to MRO, so method resolution order. So this is what we were talking about before with the inspect function, get MRO. Returns you a list of the order, the sequence of classes that will be checked for the existence of an attribute. One of the sort of grab bag of features that has been rolled into metaclasses is that you can override this. If you, for some reason, wanted a different resolution order. I don't like the fact it's called method resolution order because fundamentally it's how you access attributes on a class hierarchy. But if you wanted to change it, here is an example of a metaclass when applied to a class hierarchy. It changes the inheritance order into an alphabetical inheritance order. So it will call the class in your hierarchy with the name that's first in the alphabet first, and then it will look to the next one second. So it doesn't really matter what your parent classes are. Now, the way this works is that when the class is created, this MRO will be called, and the result will be kind of stored in an attribute called dunder MRO, which is read-only. So you can't mess with this at runtime, basically. Once you've created your class, it has even if you've given it a ridiculous order of method resolution, that's fixed, and you can't mess with it. But it's recalculated every time you update bases. Dunder bases on your class is mutable, and if you update it, even to set it to the same value that it already has, it will then call MRO again and create a new dunder MRO value. So you could actually have a function that every time you call it, changes the hierarchy of your class so that the next time you call it, it calls a different version somewhere else in the class hierarchy. And if any of you find a practical, useful reason for doing this, please tweet at me. I desperately want to find a use for this. So a common pattern that you will see in practice, going back to some more practical stuff, is that metaclasses and it will usually have a base class associated with them. People don't like setting metaclass equals. It's why you tend not to do that in daily coding. And so what happens instead is that you end up with a class called model. So this is from Django. And what it doesn't really provide that much behavior. You get the behavior from the metaclass, which is called model base. So model has a metaclass, model base, and by inheriting from model, you get the same metaclass. So that you get that behavior. The same with ABC. ABC, we're going to cover this in a second, but ABC is a core module in the Python library. That provides this ABC class. The ABC class has a metaclass of ABC meta, and so you get that for free when you extend it. So this is generally how you kind of hide your magic from your user. If you're going to be implementing metaclasses, you want to, as much as possible, hide the magic from the user. You don't want them to worry about the nitty-gritty or the fact there is a metaclass. You just explain in the documentation, hey, if you extend from model, you will get this behavior. So it all comes down to documenting the magic and trying actually to limit the magic as much as possible. And again, we'll get to that in a second. So let's talk about metaclasses in the real world for a moment, because I think that there's a general guidance around that, A, if you don't know if you need metaclasses, you probably don't. Not entirely certain that's true. And also the other bit of wisdom that goes around is just never use metaclasses, they're a bad idea. Again, like both of these are partly true, but I'm standing here giving a talk to a room full of people on how to use metaclasses. So we were talking about the uses for metaclasses. Let's see a few of these in action. So the first, I'm going to concentrate on the ABC library that comes with Python. Stands for abstract base class. It's a way of defining classes that should never be instantiated. They should be extended, and then once you've defined all the abstract features in a subclass, then that can be instantiated. And so this is an example of a metaclass that ensures that you have implemented a subclass correctly. So here I've got a class called drivable, which extends ABC. As I said before, ABC has a metaclass of ABC meta. That works in combination with this decorator called abstract method. So I've declared drive as an abstract method, which means that basically it's a placeholder, right? What I'm saying is anything that extends drivable has to implement drive if you want to create one. So just below, I've extended drivable, but I haven't implemented drive, which means that when I then try to instantiate it, I get this lovely error from the metaclass saying, hey, you haven't implemented the abstract method drive, so this is still abstract. So if I re-implement that and actually implement drive in the drivable subclass, then I can instantiate it, and then I can call drive, and it prints out driving, and everybody's happy. So and this is kind of useful, and I have to admit, I'd kind of forgotten this feature existed, and I certainly didn't know how it worked. So I'm kind of pleased to see a practical use of metaclasses in the core library. Moving a little bit further away from home, I'm going to talk about Django for a moment. Django uses metaclasses pretty extensively. There are 7 different metaclasses under the Django package in one place or another. There's also at least one more in the testing framework that comes with it. The one that people use most, and I guess I'm most aware of, is the model class and the metaclass that comes along with that. So I'm going to just roughly sketch out with some code examples what that does. So for people who haven't worked with Django recently, this is the way it works. You declare a class that really represents a table in the database. You extend models.model, and you get lots of magic behavior. The magic behavior works with fields. So these field attributes that are defined on the class are actually descriptors. So we've got one here called food name, which is a character field. We've got one called rating, which is an integer field. It's for rating food, in case anybody hadn't worked out what that was for. And then what happens behind the scenes is that inside the meta class, after the class is created, it goes through all of the fields. Well, actually, first, it registers the model with a central database. So it says, hey, we've got a new table here. When they want to create the table, when they want to run migrations, this table exists. So that's one thing that's done in the meta class. Oh, yes, and I've extracted out bits of model base here. Model base is the meta class that we're talking about. So also in new, I've ripped out huge amounts of code. There are over 200 lines of code just in that new function in model base. One of the things it does is it goes through all the fields and it tells them their name. So as I said before, this is a really common use case. So it just kind of says, hey, your name is rating, and your name is food name. So then when they come to deserialized data or serialized data, they know what they're working with. They know, hey, this is the type data that was passed to me in this constructor. This is the name that was passed to me during metaclass execution. And then in model, which has a metaclass of model base, it's adding some stuff to the class. Can't remember what that is. No idea what that is, excuse me. So I'm going to move on a little bit. We are starting to run out of time, so I'm kind of skimming a little bit. The other thing it does, it manipulates the resulting class by adding two classes to it. So it adds a does not exist class to the model class, and it also adds a multiple objects return class to the model class. And so these are specific for that table. So if you've got a high-level exception catcher for does not exist, then you can specifically say, but is it my model.does not exist? And then you know which table is missing the data at that point. So it gives you these fine-grained exceptions that are dynamically created, and they're actually created using our type class that I was talking about before. This is another case of programmatically like looping through and using type to create classes at runtime. While we're talking about Django and metaclasses, one of the things I want to really highlight here is that there's this convention that I think is just because Django's old, right? But they have this concept of creating a class inside your model class and calling it meta. And it does provide meta information about your class, like how it should be ordered, how it should be represented in different parts of the application. And it is used by the meta class on class construction, but this itself is not a meta class. It's just a class inside your other class, and it just happens to be called meta, which is not helpful when you're talking about both these concepts at the same time. And you should see the number of Stack Overflow questions that are confused about this. So having seen a couple of metaclasses and knowing how complex all this stuff is, like inheritance generally in Python, but also inheritance when it comes to class lookups and things like that, let's talk about things that are maybe better than metaclasses in some cases. So I have one update to the information I've been talking about before, which is the descriptor protocol no longer just consists of dunder get, dunder set, and dunder delete. It also now consists of set name. Dunder set name. If this is defined on your attribute, then after class creation, Python's default metaclass will just call it with the class it's been defined on and the name of the class. So this removes, from my experience, about 50% of the need for metaclasses. In the wild. It's like you no longer need a custom metaclass. You just define this on your field type or whatever it is, and suddenly you know your own name, and yeah, you don't need to worry about that anymore. Then we have class decorators. So we've probably used function decorators before. I forget the version of Python, but they also work with classes now. Function decorator is a class decorator is a function that takes a class and returns a class. Usually it will modify the class that's passed in and then return that same class. In theory, it could return whatever you like. So it could create a new class based on the class that's passed in and return that. These only affect the class that they're applied to. They don't affect subclasses. So whereas with metaclasses, they're inherited, which I maybe didn't point out enough. With class decorators, they're not. So you need to use them per class, which could be a benefit, right? It's much more explicit, and we like explicit in Python. So I would like to talk about that with these two features together. I would like to talk about how you might re-implement Django's model or something like it. Using these two features. So here I've got what I want to be able to implement. So we're using a model decorator rather than inheriting from model. And then I have to find my own fields. They just take a SQL parameter. I'm really simplifying this example. And what I want to be able to do is create a table from this. So I want to generate SQL just based on this class definition. And so by defining fields with the set name function, I can get each field to just know its own name, which is handy for the SQL generation. The decorator implementation is a little bit more complicated, only because what I want to do is add this create method and this fields method to the resulting class. So I'm essentially I'm modifying this class to add some functions to it. So the actual decorator is this block at the bottom, the actual model decorator, takes the class and it adds a create method and a fields method. And then those are just functions that are defined above. They look like methods, or they look like class methods, but they're defined as functions at the top level. And then when you use it, as I said, this is what I wanted to end up with. And what you get is this modified ranked food class with a new create method that I can then call below. Depending on the IDE you use, this can be awkward because this has no longer been defined using standard Python syntax. So anything that's doing static analysis of your code will not know that there's a create method on this class. Some of the more advanced IDEs like IntelliJ do dynamic analysis of code that's executed. Sorry, not IntelliJ, PyCharm. Do analysis of code that's executed through it, and they know what attributes are defined on classes sort of after they're realized. And so they can often provide better sort of IntelliSense for when you're writing your code. But there is I just wanted to point out there is a downside to every time you use this kind of magic, you're no longer necessarily working with the systems that help you edit code. Another option that may be better than metaclasses is code generation, which sounds horrendous, but you're almost certainly using it. This is a technique used in named tuple, attrs, data classes now, so 2 of those are in the core library. So essentially, the technique is you build a string containing the Python code you wish you had, and then you run it through exec to create the class that you want. It can be surprisingly intuitive, especially if you hide it away so that nobody knows that's what you're doing. But ultimately, what you end up with is just a class, right? You don't have a magic meta class behind the scenes. It's just a class, and you can do whatever you want to with it. And that's one of the features that they really push with attrs, is like use these decorators to essentially create the class that you want, create a whole load of boilerplate code. But once you've done that, you've just got a class. You can add methods to it the same way as you normally would and things like that, and they're unaffected. So that can be pretty cool. So just to wrap up, I can't believe how close this came to time. In conclusion, inheritance is complicated, probably more complicated than you thought. Metaclasses are really not that simple, but they're also not that complicated once you understand how inheritance works. Descriptors are definitely more complicated than they appear. And because of this complexity and all these areas that work together, you should use all of these features that I've described in this talk sparingly, or for fun. As I said, these features don't work well with code editors. They also don't work well with our brains necessarily. They work in different ways to other Python code that we might write. And so there's a danger there that you're going to build something that works in such magic ways that when it doesn't do what the user wants, they have no way of understanding why. But the last point the reason I wrote this talk in the first place was I really want people not to be afraid of this magic. Like Django has really shown how useful some of these techniques are. There's sometimes just a sprinkling of these kind of deeper magic techniques can make for a more intuitive framework or a more intuitive library. So thank you very much. I have some time for questions. I think I have 3 minutes. Did I see a hand go up over there? No? Yeah, feel free. I'll repeat there.
You mentioned that application metaclass is inherited. What happens if both superclass and subclass have different metaclasses applied? And the other is, have you ever...
Can I answer one question at a time? Because I've got to repeat that anyway. So the question was, because metaclasses are inherited by subclasses, what happens if you've got 2 metaclasses, essentially, like one class that inherits from another, they have different metaclasses. So it's the same thing as you've actually just seen, basically, which is that the lower metaclass wins. It's the most recent metaclass in the hierarchy. There are some rules about how metaclasses must inherit from each other. There has to be a linear inheritance, but I don't think I can explain it verbally. But I can point you at a blog post that does a fantastic, it does a fantastic job of explaining how that works. So the second question?
Have you ever come across metaclass or metaclass or metaclass?
So that question was, have I ever found an example of metaclasses kind of extending from metaclasses, and it's a definitive no. So I think most developers are sensible enough to kind of localize the magic as much as possible. I think one more question. Anybody? Yeah?
I'm wondering if the addition of the init subclass would remove some of the...
Yes. I totally meant to have a slide in for that. So that was a question about whether init subclass removes the need for, again, more need for metaclasses, and that's absolutely true. These are relatively recent additions to the language that are taking use cases for metaclasses and removing them. So it's like more and more metaclasses are becoming like something you probably shouldn't do. There's probably a better and more explicit way of doing what you want. That answer your question? Right.
Thank you very much, Mark. Clap.